C language is extremely flexible at handling different data types. As a C programmer, you get used to this concept, and sometimes you tend to mix those different data types without understanding what is happening underneath. And this can actually lead to many different bugs and even security problems. In this video, we would try to understand these rules which actually play underneath when you mix different data types in a arithmetic expression, or even when you are doing conversions from unsigned type to signed type. This will hopefully help us write better software, or it will help us review existing code. And before we jump into this, we need to understand that we can divide this topic into two parts. The first part, which is very essential, is to understand how does this type conversion happen? What is happening at bit level? So we will first quickly go through low level or bit level conversion, and this, once we understand this, then we can go in where and when these rules are important and when are they applied. There are two things you need to understand before we could jump into the rules which govern how type conversions work. The first one is zero extension. We want to deal with extension first. What extension essentially means is that if you have a smaller data type, say you have an unsigned character X, say it's equal to 91. 91 would be 5B in hex. So if you have a smaller data type X and you are putting 91 in it, so obviously in typical C implementations, this will take just 1 byte in memory. But if you put it in a variable which is integer, say 4 bytes, and you do y is equal to x, what essentially would happen is that this value 91 would suddenly be converted into an integer. But here, because it's unsigned type, it would be appended by zeros, and this is called zero extension. So this is a lossless conversion where the value remains the same, but we just put zeros in the preceding bytes. So in memory, we'll have 4 bytes. Of course, so if you have a train of memory, so for example, in memory, the first byte whose address is 0 starts here. The second byte whose address is 1 starts here. The third byte whose address is 2 starts here. And the fourth byte whose address is... So in memory, the order of these bytes is usually dependent on what type of platform it is. For example, if it is a little endian machine, then the least significant bit comes first, and then the second least significant bit, and then the third one, and then the fourth one. But if it was a big endian machine, the big endians are less common nowadays, then it would have been placed so that the most significant bit would go first. But for our discussion, let's keep it simple and let's not worry about endianness of an architecture. So if you are in short summary, if you are putting a smaller data type into a bigger data type, and you append zeros to it, this is zero extension. One important question which might arise is what happens to signed numbers? Before we jump into that, I want to discuss a quick property with you about signed encoding, or the most commonly used signed encoding called 2's complement. Say for example, if you have, let's for this discussion assume that C has a data type which is in which has 4-bit length. Say for example, you have a number 1010, and it's a signed number. Suppose it's called nimble data type, and it is x equal to 10, right? It's an unsigned. Now let's assume for a second that this can even have a signed encoded data type. Then that would be signed nimble x is equal to same bit pattern. What would be the same bit pattern in signed encoding? Let's assume for a second platform is using 2's complement, which is most common encoding used for negative numbers. So the most significant bit is a sign bit. So the weight is negative, -8. This is 0 and this is 2. So obviously the value is -6. So for a 4-bit data type, this is -6, right? 1010. Let's append 1 to it and make it a 5-bit data type, right? What is the impact of appending 1 here? If we assume for a second we keep it signed encoded with 2's complement methodology, what happens here is this -8 weight becomes positive and this weight here goes negative, and this is of course 2. So the value essentially remains the same because these two are -8. Even if you add one more here and make it a 6-bit data type, the impact is so much so that, so for example, the weight here turns -32 because now this one is a sign bit and this weight goes positive and this is also positive. So all these together still remain -8. So if you keep on adding 1 here and you keep using the same encoding 2's complement, the value never changes. And this is sign extension. So if you have a smaller negative number in C, for example, on typical implementations, say you have signed char x is equal to -5. Now first thing we need to figure out, how do you represent -5 in a bit pattern? Now, a simple trick is, of course, that it's a manual trick. You represent 5 first in, first figure out what is the bit pattern for 5. It is this, right? 101. First, you flip all the bits. And then in the second step, you add 1. So this is the binary representation of -5 in 2's complement. Because this signed encoding, signed data type is of course represented in 2's complement. Now this, if we want to, it's easier to talk about these bit patterns in hex. So this would be F and this would be B. So in memory, this, we can say that this is FB, right? Now if we have another data type, int y, and we say int y is equal to x. So essentially we are putting a smaller data type into a bigger data type. So this is extension. And when extension happens with signed encoded data types, smaller data types, sign extension happens. So what happens here is that the first byte was FB, right? So the first data type was 1111 1011. If you recall, this is a signed character. So this is sign bit. So when you equate it to y, what happens is that this sign bit is extended. We want to, these conversions, C standard tries to keep them lossless. That is, the -5 remains -5. To keep -5, you keep appending ones to it. We just saw that if we add ones to the bit pattern, the value remains the same, right? So what happens is this FB becomes FB first byte, FF second byte, FF third byte, FF fourth byte. And as you know, this F is actually 4 ones, and this this another f is 4 ones, and then this would be 4 ones. So similar. So essentially, sign extension means that you keep prepending, you prefix them with as many as ones as you need to fill 4 bytes here. And this is sign extension. Now there is another side to it. What happens if you want to, if you typically put a bigger data type into smaller data type? Say for example, you have, that is called truncation. Of course, truncation is simple. So typically what happens is that if you have, for example, -1, and it's an integer. Now integer -1 would obviously be 4 bytes. It would be all ones. And if you have another data type, say X character, and you equate, what happens essentially is these bits get truncated, and what is left is all ones. So then the value remains the same. Now X is also -1. And this is truncation. This is what typically happens on most implementations of C. But of course, with unsigned encoding and with unsigned numbers, the encoding is different than signed numbers. And signed encoding is typically 2's complement, but that's not in the standard. Standard says it could even be 1's complement encoding, or it could be signed magnitude encoding, but typically it's 2's complement encoding. Now that we have got a glimpse of what happens at the lower level, how does these conversions happen, it's good to discuss the rules which play while we do these conversions. While doing programming, there are times when we need to convert source C type to a destination C type. It could be because of implicit conversions. For example, whenever we call a function and supply arguments, then the argument get implicitly casted to the type of the actual arguments in the function definition. Or it could even be assignment operator. For example, you assign a source C type to a destination C type, or it could be a function call where function returns some type and the variable which captures that return type has a different type. Now, as long as the main thing to remember here is that if the destination type can hold the value of the source type, then source type values are semantically preserved always. Another way to look at it is, for example, if you have a line number and you can think of ranges. For example, you have a source, say it's a signed character. Now signed character ranges from 127 plus to -128. And the destination is, for example, a short, say signed short. Because it's 16-bit usually in most implementations. Of course, all the bits which fall in this range when source is converted to destination will be preserved. And this can even hold for different signed data types. Say, for example, if the destination is a character, a unsigned char. Now, for unsigned char, we know that the value it can store is from 0 to 255. So only range which intersects with signed character is this much. So as long as source has a value in this range, it would be preserved fine. What happens if the range of values are outside this area? Let's quickly discuss that. Let's say if destination is a unsigned integer. And this could be anything. Now, if the source number could be represented, for example, in 3 bytes, and the destination size is, say, 4 bytes, then it's straightforward, right? The conversion will preserve the values. But what if the source is 6 bytes long and destination is, remember, unsigned? So what happens usually in most implementations is that these 2 bytes get truncated and the value is then converted to destination. What if the source is signed, not unsigned? This example is for unsigned source and unsigned destination. What if the source is signed and the source is bigger than destination? Then the standard says you keep adding or subtracting with 2 raised power width of type till it falls in this range. What that essentially means is that, for example, say for example you have an unsigned character and you have a signed value, say 1025. This would be 1 followed by 1 followed by 9 zeros and 1. Or you could even write it as, I think, this 401 in hex. Now, the destination here is character, unsigned character, so it can only store 8 bits. In this case, because it's a signed, let's assume it's a signed short. So what will go to the destination? In most of the common implementations which use 2's complement to represent a signed short, what necessarily happens is that the top bits get discarded and the values transfer. But even if we follow the standard says you keep subtracting or adding 2 raised power w. W is 8 here to this value till it falls in the range. Say now it's a big value, it's quite big, so we'll keep subtracting it with 256 and it should fall in the range. If we subtract, say, this 3 times, it will be 257. So, but 257 doesn't come in the range. The highest value this unsigned character can store is from 0 to 255. So we need to subtract it 1 more time. Okay, 1. As you can see, the 1 is correct answer, even after we truncated the top extra bits here. So as long as the destination is an unsigned integer, everything is defined. It's defined, the values might be unexpected, but they are defined in the standard. But as soon as your destination integer is changed to signed integer, then things can be implementation defined. For example, if source is bigger, say this is 4 bytes of source and the destination is just 2 bytes, then the according to C standard, this conversion is implementation defined. So implementations would do it in a certain way, and they will of course ideally define it, but it won't be portable at all. Of course, if source is smaller, say source is 2 bytes long and destination is 4 bytes long, then we do sign extension from source signed value. As we just discussed, that extending by 111 doesn't change this value as long as the underlying value is represented by 2's complement. Now that we have discussed the low-level details of integer conversion, it makes sense to discuss the rules. Before we discuss the rule, there are two things you need to remember. One thing is about integer promotion. So every time there are operators working on operands, and operands have data type bool, char, or short, be it signed or unsigned, they will always be promoted to integer. In rare case, they are promoted to unsigned integer. We will discuss those cases shortly, but in most of the cases, every time you see an operator working on an operand, and operand is of character bool, char, or short, anything lower than integer. So short, be it unsigned or signed, char or bool, all these will be promoted to integer, and this is called integer promotion. This is a very important C standard concept. And there is another thing which you need to remember before we discuss usual arithmetic conversion rules, that is conversion ranking. So as soon as you deal with integer promotion, the next thing you need to deal with is data types which are higher than integer and integer itself. For example, int, long, long, long. Now, even though I write int, long, 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 both unsigned and signed variants are should be taken into account here. So as soon as you have dealt with data types which are smaller than integer, signed or unsigned short, signed or unsigned char, we need to check the remaining data types, integer, long, long, long. So the first thing to remember is conversion ranks. So C standard ranks the data types. Now integer has the lower rank, then long, both signed and unsigned, and unsigned and signed, long, long. We'll shortly see why it is important. So as we discuss, the first thing which happens every time we need to think about these rules is integer promotion. So if you have an operation x asterisk y, and one of the data types is lower than integer, say short, unsigned short, signed short, character, unsigned signed character, or bool, they are promoted to integer, and that is integer promotion. Say x here is unsigned short, and say y is an integer, signed integer. So x will, before this operation takes place, x will be promoted to integer. So, and this would be signed integer. By default, it's signed integer, as long as the signed integer can hold all the values which x can have. The conversion happens to signed integer, because unsigned short will have obviously from 0 to 2 raised power 16 minus 1 range of values, and this range is obviously the C standard says that signed integer can hold this range. So obviously the conversion happens to signed integer, and that's usually the obvious case. But there could be corner case implementations, C implementations, where the instead of integer, the integer promotion will happen to unsigned integer. One of the examples could be, say you have a C implementation where the character data type, instead of stored in 1 byte, it's stored in 4 bytes. And this is possible. C standard allows this, but the typical C implementations don't have it. Character is usually 1 byte, but for the sake of discussion, let's assume there's a C implementation which has character data type with 4 bytes. So unsigned char will obviously have a range of 0 to 2 raised power 32 minus 1. And signed integer obviously won't have that range, that can't have that range, because the range of signed integer is from minus 2 raised power 31 to 2 raised power 31 minus 1. Because of this reason, because integer promotion is always designed to be lossless, if you have an operation x, maybe asterisk y, where x in this implementation is an unsigned character, then this would be promoted to unsigned integer. We just spoke a while back about conversion ranking. In C standard, all the data types are ranked according to this ranking. We have bool, char, short at the bottom, and then we have integer type, long type, and long type. And of course, unsigned and signed types for long and other types have same level of ranking. So this ranking is quite important when we are doing this usual arithmetic conversions in when we are applying an operand to a couple of operators in an expression. So we just need to remember this conversion ranking while programming. Ideally, in an ideal world, you don't need to even remember the bottom 3. So because as we discussed a while back, that integer promotion takes care of promoting all the types which are below integer to integer. So everything here, bool, char, short in a expression is first converted to signed integer. In an odd case, it can even be converted to unsigned integer, but that's the first step. So the first step of in usual arithmetic conversion is integer promotion. So the first thing is integer promotion. So if you have, for example, let's simplify this. We have 2 operands and we have an operator. Let's assume that integer promotions has already taken place. Now what happens after that? There are 3 cases to consider here. First case is when both these operands have same signedness. For example, if x is signed, then y is also signed. If x is unsigned, y is also unsigned. So they have signedness is same. That's the first case we should consider. The second case is when one of the data operands is unsigned and its ranking is higher. So unsigned ranking high. And the third case, or equal to other operand. And the third case is when one of the operator has signed encoding and the ranking is high. Signed encoding, ranking high. Now these are the only 3 probabilities here. For example, the first probability is when both of them are either signed or unsigned. Now we are left with only one other probability, that one of them is signed and the other is unsigned. And in that case, if the operand which has unsigned encoding has ranking higher or equal to other one, that is one case. And the last case is when one of them has signed encoding and the ranking is high. So let's take them one by one. Let's say we have, this is the easiest case. Signedness is same. So in that case, in all cases, we actually need to find common type for the operator. And this common type is the type to which all operands are converted to. For example, if we have unsigned char x, sorry, not char, because char is already gone by this time because of integer promotion. Unsigned int x, and we have unsigned long y, then x plus y has common type unsigned long, because unsigned long has higher ranking in the ranking hierarchy. And same could be said if both are signed. Then the common type for xy would be long type, and both of these arguments operands would be converted to long, and after that addition will take place. So having same signedness is an easy case. What if they don't have same signedness? Then we have two cases, right? One of them, so if they don't have same signedness, one of them is unsigned, the other is signed. And then we have two cases. What if unsigned has greater ranking or equal to ranking compared to, say, unsigned is x, then y, it has greater or equal to ranking than y. The case could be, for example, x is unsigned long and y is an int, right? So unsigned long has higher ranking than. In that case, the common type is obviously unsigned long. There could be even an other case. For example, x has type unsigned int and y has type int. Now in this case, the ranking is same, right? Even then, unsigned wins. So every time one of the operand is unsigned and the ranking is high or equal to the other operand which is signed, then common type is unsigned operand's type. So in this case, x and y both would be promoted to unsigned integer. Of course, x is already an unsigned integer, but both would be first promoted and then the operation would take place. Now the last type, in the last type, one of them is signed and has higher ranking. This is a tricky case. Even though x, for example, in this expression has higher ranking and is signed, it doesn't mean in all cases both of these operands would be promoted to signed type. For example, let's say on a 64-bit very common architecture, we have long is 8 bytes and integer is 4 bytes. As long as signed type, which has higher ranking, can represent all the values of other operand, the common type is the type of this signed operand. Let's say x is long and y is unsigned integer. right? So in this case, long, which is signed, can represent all values in the range of y, unsigned integer, because unsigned integer on a 64-bit system is 4 bytes. So the common type for this expression is long. So y would be promoted to long type, and then the operation will happen. But on a 32-bit system, long is 4 bytes. A typical system these days. Long is 4 bytes and integer is 8 bytes. Now here, x actually, even though signed and has higher ranking, can't represent all values of y, right? Because it's unsigned integer encoding, and it has a range on the positive side far higher than x. And both are, sorry, I was wrong here. Integer is also 4 bytes. So x can't represent all values of y. In that case, instead of having, so in that case, both of these operators are promoted to unsigned variant of the operand with higher ranking. This is the most complicated part. So when promotion happens, even though x had a type long, which had higher ranking, but because x can't represent all values of y, x is itself promoted to unsigned long, and y gets promoted to unsigned long, and eventually the operation is performed. So this gets quite complicated as soon as one of the operand is signed and it can't represent all values of the other operator. This covers everything which one needs to do usual arithmetic conversions properly. Integer promotions, conversion ranking, and the rules which represent common usual arithmetic conversions according to C standard. There are still undefined behaviors or examples which one could look into, but that would be part of future videos. Thank you very much.